Okay, in the last class we have discussed about the rock algorithm, rock clustering method. So I'm just um, go through the example again. So here we have considered some objects or records. And initially, the rock clustering algorithm, since it is a kind of agglomerative hierarchical clustering, initially each object is considered as a cluster. Initially, each object is considered as a cluster. So initially, there is only one element in the cluster. There is only one element in the cluster, and after that, we need to match the clusters based on the similarity. That similarity initially can be obtained from this Jaccard coefficient, and after that, based on the value of the Jaccard coefficient, we can get uh, from that we need to calculate the number of neighbors and number of links, and by using the number of links, we are going to calculate the similarity. What is that? Uh, Goodness measure, and based on the goodness measure only, we are going to merge the clusters. So here we have first calculated the similarity matrix. We need to generate the similarity matrix between every pair of clusters. And after that, from the similarity matrix, you can generate the adjacency matrix based on a similarity threshold. For this example, they have given 0.3. So before generating the adjacency matrix, the values, the similarity values which doesn't satisfy this threshold should be neglected. So those particular values are replaced with zeros, and all the remaining values are replaced with ones. And this is the adjacency matrix obtained. And after that, we need to square the adjacency matrix to get the link matrix. So from this link matrix, you can able to generate this goodness measure. So these are all the resulted goodness measures. And if you observe that the highest measure is obtained for these particular pairs, which means that these pairs are, that means it is good to merge these clusters. So you can select in the first step, as a first step, you can select any one of that pairs. And here in this example, they have selected this pair. So now this P1 and P2 become one cluster, and P3 is in another cluster, and P4 is in another cluster. How many clusters are there here? In the previously we're having 4 clusters. Now we are merging these two as a single cluster. Now we are with the 3 clusters. Our intention is to derive, that means to repeat this process until the number of clusters become 2. That means again you need to repeat the process, and you need to merge any one of this P3 or P4 with this C1 or whatever. You can merge C2, C3 into a cluster or whatever, depends upon the further obtained values. So here we are with 3 clusters. Again, for these 3 clusters, you need to derive the link matrix from the initial link matrix. No need to again go for all the calculations. We are already having the initial link matrix, and from that you need to derive this new updated link matrix. And from that link matrix, again by going through the formula of the goodness measure, you need to calculate the goodness measure for the pair of clusters. And based on that, which is having the highest measure, this one is having the highest measure. So you need to club this P3 with the already existing cluster P1, P2. So now this P1, P2, P3 become one cluster, and this P4 become one cluster. So since we have left with only 2 clusters, which is actually needed, so we can stop the process here. So this is all about this. And here we have another example. So 2 records we are having, and from that, based on the similarity, not 4 records, A, B, C, D, 4 records we are having, and from that we need to calculate the similarity among the observations or objects. And from that similarity, you need to first derive the similarity. What's it? Adjacency matrix you need to generate, and from that adjacency matrix you need to generate the link matrix. So this is the similarity matrix. And from this similarity matrix, based on the given threshold 0.2, this is the generated what? Link matrix. So from this generated link matrix, you need to next construct the goodness measure for every pair of clusters. And based on, as done for the previous example, based on the goodness value obtained, you can gradually club the clusters. And finally, after doing that, this is the result. Resulting clusters after applying rock. This is the result after this. So this is your next assignment. So what is our previous assignment? Previous task. Assignment ante confuse avutunnaru. What is our previous task given? Last class lo, last not la, exactly last class. Previous class lo assignment ichchanu kada. Class assignment. What is that? Alexia. గుర్తుందా ఎవరికైనా ఏంటది? I think K-means algorithm. That is about K-means algorithm. That one of your group need to share the screen regarding that K-means. And this is your next assignment. Screenshot తీసుకోండి. Here is a problem and here is a solution too. Problem is given, 4 records are given, and Jacob coefficient is also given. Solution is also given here, right? I want the step-by-step process of obtaining the two clusters A and BCD. A procedure మీరు సాల్వ్ చేసి నేను అడిగినప్పుడు స్క్రీన్ షేర్ చేయండి. And in this class, at the mostly in the middle of the class, I asked one of you to share the randomly. I asked one group to share the screen regarding the K-means. I think then 2 assignments ichcham previously. I remember like that. One is K-means and other thing I don't know. I don't remember. I need to go back. And in this assignment, in this class, in the middle of the class, one of you need to share the screen regarding that. So now we are going to have the, because this is the actual procedure. What we have done is the actual procedure for raw clustering algorithm. Now we are going to have the procedure, have the algorithm for the rock algorithm. We are having the step-by-step procedure for the rock algorithm. So here for this, you need to consider initially some random sample you need to take. That sample is represented with S here, and K represents the number of clusters. So first of all, you need to know the total number of clusters. And after that, for all points, so we need to treat all the sample points as a individual cluster. And we need to compute the links among the clusters in the sample data. So we need to compute the links for all these S sample points, and we need to store that in the link. And for that, now we need to build the local heap for each cluster, and we need to build the global heap for all the clusters. So 2 heaps we need to build here. We need to build the local heap. Similarly, we need to build the global heap. So here, excuse me. So look at here. So here, local heap, let's say it is Q of I, is maintained for each cluster. For every cluster, you need to maintain the local heap. So a cluster J is added to the local heap of I if and only if link of I comma J exists. So first you need to create local heap for each cluster, and after that, if at all you are having the link for that cluster to with another cluster, that cluster is also added to the local heap of this particular cluster. For example, you are having cluster C1 and this is cluster C2. You are having this, some points it is having and some points it is having. You are going to construct the local heap of cluster C1, and you need to add all other clusters to this. Which cluster is having, suppose this is having link, the C2 is having link with C1, so you can add C2 to this. Some other C3 is there and it does not having any link with C1, so no need to add C3 in local heap of C1. So like this, you need to add the all remaining clusters to the local heap whenever we're having a link between those two clusters. And next, after adding all the clusters in the local heap Q of I are ordered in descending order based on their goodness measure. So this is about the local heap. First, we need to create the local heap for each cluster, and after creating, we need to add all the clusters to that particular local heap. Uh, that means we need to add all the clusters which are having direct links with that particular cluster. Suppose cluster A is there, and we need to first create the local heap for this particular cluster, and we need to add all other clusters which are having links to this A into that local heap. And after adding all the other clusters, we need to sort the elements of the clusters, elements of local heap in descending order based on their goodness list. And similarly, coming to the global heap. Similarly, I'm not explaining in depth regarding this algorithm because the procedure, exact procedure, we already go through all these things. Just I'm for understanding purpose only, I'm briefly explaining this. So with this algorithm, we have finished with rock and we can go for the other algorithm, no problem. So try to understand what I'm saying. This is little confusing. So coming to the global heap. So global heap is generally created or maintained for all the clusters. That means how many number of clusters we are having, that many number of clusters are there in the global heap. And after that, all the clusters in the global heap are ordered in descending order based on the goodness measure. So here we are building the local heap. So for building the local heap, we need to have the link information. Why? Because for building the local heap, every cluster which is having link with that particular cluster has to be added to that local heap. That's why we need to have the link information and we need to have the particular cluster for which you are going to build the local heap. And after that, coming to the process of constructing global heap, you need to have the entire sample and you need to have all the local heaps for building the global heap. So here, our task is to repeat the process until we get the k number of clusters left in the global heap. Initially, we're having n number of clusters in the global heap since there exists n number of sample points. So we need to repeat the process until we get the k number of clusters, until we left with the k number of clusters. That's why uh, we need to have this condition. And first, in each step, maximum cluster u in Q and maximum of Q of u has to be taken, and they are the best clusters to be merged. So first we need to identify the maximum cluster in Q. Let us say this is u, and based on that you need to go for the local heap of this u. So this is the local heap of this u, and maximum of all the clusters here we need to identify it as v, and we need to merge this both u and v. And after merging, after creating a new cluster, we need to remove the individual local heaps, individual clusters u and v. You need to remove from the global heap. So here the same thing we have did through the algorithm here. So first we need to identify the maximum, that means largest cluster in this particular global heap. How to identify the maximum? Because we have already sorted the elements in descending order based on the goodness measure. How to sort in the sense? We already know that how to calculate the goodness measure for all the pairs. How to calculate the goodness measure for all the pairs? We already know that. We need to sort them first in descending order. That automatically top of the list consisting of the cluster pairs which is having the highest goodness measure. So we need to directly take the maximum element, in the sense the cluster which is having the maximum goodness measure. So that we need to identify. So based on that particular cluster, you can go for the local heap of that, and we need to identify the maximum element. So let us say this is V, and before merging U and V, we need to delete that from the global heap. We need to delete that V from the global heap, and after that you can merge these two, and W is created. And after that, we need to remove the local heaps of both U and V from the global heap. That is what here it is. Deallocate Q of U and deallocate Q of V. We need to deallocate these local heaps of U and V from the global heap. And before that, we need to update all link information, and we need to associate all the link information of U and V to the W. For example, if you have a linked list, suppose this is a list and linked like this. If at all you want to remove this, you need to, before removing that, you need to connect the links. Suppose you are having a double linked list. You want to remove this particular middle list. So before you remove that, you need to connect the links directly to the adjacent list, right? Then only you can remove this. So here also, before deallocating these two things, first you need to connect the links of all U and V to the W. So here, let us say X is a cluster which belongs to both local heaps of U and V. So here, the link between X and, that means the number of links between X and U and number of links between X and V become the number of links between the X and W. And after that, from the local heap of X, you can remove U. Similarly, from the local heap of X, you can remove V. And after that, we need to insert this new W is the new one, right? You need to insert this W into the local heap of X. And again, you need to insert this X to the local heap of W. And you need to update that in the global heap also. So in this way, the algorithm proceeds. And here is a process of calculating the link information, which we already know. And this is some pseudocode is given here. So coming to the conclusion, ROC is a clustering algorithm designed to deal with categorical data, especially for categorical data. So it uses novel concept of links to measure the similarity between data points. So ROC performs well on real categorical data and respectably on time series data. Especially it also performs well on time series data. So it scales well to the large data sets. And it depends on the value of K, that means the number of clusters, and high worst case complexity. So this is all about the ROC algorithm, especially what are the takeouts from this ROC algorithm. So it is works good for categorical data, and it also suits for large data sets, because only we are clustering the sample of data. So it's also suitable for large data sets. And after that, especially for categorical data, it can handle efficiently, and it considers instead of distance metrics, it considers the link measure of similarity, and it has the goodness of measure, which will effectively produce the best number of clusters to be matched. So this is all about ROC method. And now we are having two methods under hierarchical clustering, Batch and ROC method. We have finished the topic of hierarchical clustering. Now we have a density-based clustering algorithms we are having. One of that algorithm is DBSCAN. DBSCAN is one of the density-based clustering algorithms. So what is the density-based algorithm, Steve? So density-based, we have already have different kinds of clustering algorithms. Model-based is there, grid-based, partitional clustering, hierarchical clustering. Similarly, we are having density-based clustering. The description about each and every method briefly is already discussed in the previous classes, right? So here, DBSCAN density-based in the sense, now it doesn't consider any kind of distance measures, or it doesn't go for partitioning the data or like that. It only considers the density. Density in the sense number of points in a given space like that. So it purely considers the density of the given data, and it forms the clusters based on the density. So the major advantage of this is it can generate the arbitrary shaped clusters. Whereas in case of previous clustering algorithms, all those algorithms generate only spherical shaped clusters. Even ROC also, right? All those clusters generate spherical shaped clusters, whereas this DBSCAN generates arbitrary shaped clusters. So because it purely considers density only. So let us go through the details, go into the details. So this DBSCAN is abbreviated as density-based spatial clustering of applications with noise. So it's a density-based clustering algorithm. So the algorithm grows regions with sufficiently high density into clusters. So wherever it finds some high dense area, it forms that into a cluster like this. So it discovers clusters of arbitrary shapes. Finally, the final thing is how it defines a cluster. So it defines a cluster as a maximal, just observe these lines, as a maximal set of density connected points. So it defines a cluster as a maximal set of density connected points. For example, we're having points like this. By seeing itself, we can't say that which are densely connected and which are not densely connected. If suppose we are having points like this, so I can say that these are densely connected and these are not. Why? Because the remaining points are completely sparse with respect to this clustered points. If at all the data set is like that, there is no problem. But if at all the data set is like this, then how can we form the clusters from this kind of data set? So by projecting the data into the scatter plot, we can't say that which points are densely connected. Densely connected in the sense they are connected in a dense area. By seeing itself, we can't say. So we need to go through some procedure and we need to evaluate or we need to calculate actually which points are really densely connected with each other. For example, by going through certain procedure, I observe that these points are densely connected. By going through certain procedure, I observe that these points are densely connected. Now I can form clusters with these points. And I left these points as, I treat those points as outliers. So here I don't want any kind of distance measure or any kind of similarity or link similarity measure. I don't want all those points because I'm not calculating I'm not considering certain boundary here. So here I'm only considering the density of a region. So density of a region in the sense that region boundary we need to consider here. That region space we need to consider here. Let's go to the details, and before that we need to know about the basic definitions used in DBSCAN algorithm. So these are some basic definitions we're having. Here, the neighborhood. Now, are you able to follow?
Yes, ma'am.
మీకు రాక్ అల్గరిథం కొంచెం డిఫరెంట్ కైండ్ ఆఫ్ అల్గరిథం అండ్ లిటిల్ డిఫికల్ట్. సో మీకు ఏదైనా ప్రీవియస్ అల్గరిథం అర్థం కాకపోతే దాన్ని అక్కడితో వదిలేయండి. మీకు ఇంట్రెస్ట్ ఉంటే అడగండి నన్ను, ఇంకో క్లాస్లో అడిగినా ఇంకోసారి చెప్తాను, పర్సనల్గా అడిగినా చెప్తాను, ప్రాబ్లం లేదు. మీకు అది టఫ్గా ఉంది కాబట్టి దాని ఎఫెక్ట్ నెక్స్ట్ క్లాస్ని చూపించదు. మీకు ఒక ఎగ్జామ్ సరిగ్గా రాయకపోతే నెక్స్ట్ ఎగ్జామ్ మీద దాని ఎఫెక్ట్ పడితే ఏమవుతుంది, నెక్స్ట్ కూడా ఫెయిల్ అవుతారు. సో ఇక్కడ ఏదైనా ఒక ప్రీవియస్ అల్గరిథం ఏదైనా అర్థం కాలేదు అంటే లీవ్ ఇట్. మీకు తర్వాత క్లాస్ అయిపోయిన తర్వాత అడగండి, లేదంటే అక్కడే క్వశ్చన్ రైట్ చేయండి. అడిగే ఇది లేదు అంటే తర్వాత క్లాస్ అయిపోయాక అడగండి, నో ప్రాబ్లం. ఇది చాలా సింపుల్ అల్గరిథం, చాలా ఇంపార్టెంట్ అల్గరిథం. సో ట్రై టు కాన్సన్ట్రేట్ ఆన్ DBSCAN. ప్రీవియస్ అల్గరిథం లిటిల్ టఫ్ రాక్. సో నేను దాన్ని బ్రీఫ్ గానే చెప్తాను. అందుకని ఈ అల్గరిథం చాలా సింపుల్, ఈజీగా గుర్తుపెట్టుకోవచ్చు, నేర్చుకోవచ్చు, అర్థమైంది కాబట్టి, అండ్ ఇంపార్టెంట్ కూడా, అండ్ ప్రాబబ్లీ repeatedly it is asked in the final exams also. So try to listen this, try to follow this. One second. Pinky is there?
Ma'am.
Ma'am, number 21 ని నా క్లాస్ అయిపోయాక కాల్ చేయమని చెప్పండి ఒకసారి.
Okay, ma'am.
So here we have some basic definitions. Here we have some basic definitions used for DBSCAN on them. So coming to the epsilon neighborhood. Coming to the epsilon neighborhood. What is this epsilon neighborhood? And core object is there, and directly density reachable, and density reachability, and densely connected. All these definitions you need to know. And finally, by going through all these definitions, you can able to know what is a density connected point. How can we say certain points are density connected? Why? Because our ultimate goal is you need to have all the density connected points. You need to identify all the density connected points, and you need to form the cluster with that point. So our ultimate goal is to identify the density connected points in a space or in a given data set. So to know how to identify the density connected points, we need to go through all these above definitions. So first one is epsilon neighborhood. So the neighborhood within a radius epsilon of a given object is called the epsilon neighborhood of an object. Suppose I have some set of points and just I'm forming, sorry, so leave that. So here I'm having an object here. This is, let us say, this is P, and here also I'm having certain points, and here also I'm having an object Q. These are all points in space. Okay. So here the neighborhood within a radius epsilon of a given object. Suppose this is the object constraint. So from this object, take the radius. Take the radius. Wait. Take the radius epsilon and draw the circle. Draw the circle with the radius epsilon. Epsilon is given by the administrator or the user, programmer, whatever. So this neighborhood which is drawn, this is called as a boundary, right? This is called as a boundary. So this neighborhood which is drawn by taking the epsilon radius is called as the epsilon neighborhood of an object P. Epsilon neighborhood in the sense, did you know that, just wait a second. Did you know about the magnetic field? Are you heard the term magnetic field? Anybody?
ఎస్ మ్యామ్.
మీకు తెలుసని చెప్తున్నారు మేడం, తెలుసా తెలీదా?
తెలుసు మ్యామ్.
ఏంటి మ్యాగ్నెటిక్ ఫీల్డ్ అంటే? వాట్ ఈస్ దట్?
అంటే ఒక సర్టెన్ ఏరియా మొత్తం ఆ మ్యాగ్నెటిక్ ఎఫెక్ట్ ఉంటుంది మ్యామ్.
మ్యాగ్నెటిక్ ఎఫెక్ట్ ఎంత ఏరియా వరకు స్ప్రెడ్ అయి ఉంటుందో ఆ ఫీల్డ్ మొత్తాన్ని మనం మ్యాగ్నెటిక్ ఫీల్డ్ అంటాం. Similarly, here also we are considering certain space spread around a particular object. In there, certain space we have considered around a magnet. Here, we are considering an object, and we need to consider the certain space around that object. How much space? That is the space having the epsilon radius. The circle which is with the epsilon radius. So if you consider this is that object, if this is the, sorry, if this P is the object, we need to, from P we need to draw the epsilon radius and we need to draw the circle. Suppose here this is my object, this is some Z, this is my object. From this I need to consider this epsilon radius and I need to draw the circle, whatever may be the object. There is no rule that you need to consider that object itself. There is no rule like that. You need to consider one of the object. You have many data points, right? One of the data point you need to consider, and from that data point with the epsilon radius you need to draw the imaginary boundary. So that is called as an epsilon neighborhood of a object P. So here, if suppose this is the Q, So this particular boundary is the epsilon neighborhood of the object Q. So this is about the epsilon neighborhood. And next, if what is the core object? What is the core object? If the epsilon neighborhood of an object contains at least a minimum number of, which is called as min points. Min points is nothing but minimum number of points. So if an object contains a minimum number of points, then the object is called a core object. So if the epsilon neighborhood of an object contains at least minimum number of min points. For example, suppose my min points are 3. My min point value is 3. Given value for the min points is 3. That means what it means? The epsilon neighborhood of any object should consisting of minimum of 3 numbers, so 3 number of points along with that object. For example, consider this case. Here we are having within the epsilon neighborhood of P, how many objects we are having? This is 1, this is 2, and this is 3. Here it satisfies or not? This particular condition is satisfied or not? Now, here within the epsilon neighborhood of an object, some x number of objects should exist. If that is the case, we can call that object as a core object. X in the sense, some minimum number of objects along with that P, we have that minimum number of objects within the epsilon neighborhood of P. Then we can say that P is a core object. For example, this is 4. We are having minimum points as 4. So how many points are there in the epsilon neighborhood of P along with P? How many points are there in the epsilon neighborhood of P?
3, ma'am.
3 points are there. But what are our minimum points given?
4, ma'am.
4. So it does not satisfy the minimum points. So we can't say P as a core object. We can't say P as a core object here. Whereas in case of Q, how many points are there in the epsilon neighborhood of Q? How many points are there in the epsilon? Yes, 4 points. So it satisfies the
Minimum
requirement. Yes. So now I can say that Q is a core object. So here Z is also there. So how many points are there in the epsilon neighborhood of Z? How many points are there in the epsilon neighborhood of Z?
2, ma'am.
2 points. So it also does not satisfy the requirement, minimum requirement. So here out of all the objects, I only found, for now, I found only 2 objects. Or you can check with the other objects also. Many objects you are having here, right? You can check with the other objects also. Suppose consider this object and take the radius epsilon and draw the epsilon neighborhood. So here draw the epsilon neighborhood. For example, this is the epsilon neighborhood. So how many points are there? Let us say this is x. How many points are there within the epsilon neighborhood of x? Ennunnai?
1 only, ma'am.
Chudandi ikkada. This is 1 point, and here also it touches this, right?
Okay. 2 points,
Yes,
ma'am.
2 points are there. Yes, 2 points are there. But 2 points are there, but it does not satisfy the minimum requirement. So it is also not a core object. So core object is nothing but an object which consisting of minimum points or minimum number of objects within its epsilon neighborhood. That object is called as a core object. Let's coming to the other one, directly density reachable. So given a set of objects D, we say that an object P is directly density reachable from the object Q if P is within the epsilon neighborhood of Q and Q is a core object. So here Q is a core object, right? In this example, in this case, Q is a core object. So what are the directly density reachable objects? So let us say this is some A. This point is some A. So I can say that A is directly density reachable from Q. So if I want to say that A is directly density reachable from Q, first thing Q is a core object. So here in this example, Q is a core object or not?
Core
Q is a
object.
core object. Yes, core object. Q is only the core object. In this example, we found that Z is not a core object, P is not a core object, and X is also not a core object. So Q is only the core object. And here I can say that A is directly density reachable from Q based on the two conditions. My first condition is Q should be a core object. So we already know that Q should be Q is a core object. So first condition is satisfied. And the second condition is A should lie within the epsilon neighborhood of Q. That means a Q circle undi kada dantlo A one of the object ayi undali. That is my second condition. Then I can say that A is directly density reachable. Simply just compare this example with the magnetic field. So here is a magnet. I assume that this is the magnetic field based on the magnet capacity or size of the magnet, whatever. This is the magnet. I assume that this is the magnetic field. And here is some other point which is A. And I can say that A is directly within the reachability of Q. Why? Because this is within the magnetic field. This stays within the magnetic field and Q is a magnet. Since Q is a magnet and A is placed within the power of that magnetic field, I can say that A is directly connected to Q like that. For example, I'm telling. So here also, to say that A is directly density reachable from Q, first condition is Q is a core object and second condition is A should be lie within the epsilon neighborhood of Q. So let me read the statement again. So here an object P is directly density reachable from object Q if P is within the epsilon neighborhood of Q and Q is a core object. Is it clear or not? Is it clear or not? Or you want me to repeat?
Clear, ma'am.
Yeah. So that is directly density reachable. And the next one, density reachable. Density directly in the sense directly the word if the directly that word is absent, which means that indirectly density reachable. Directly is not there, then you can treat it as indirectly density reachable. So the next definition you need to know about is an object P is density reachable. That means an object P is indirectly density reachable from the object Q. When it happens, an object P is indirectly reachable from the object Q. When it happens means here, let us say here you have a set of points, some P1, P2, P3, P4, like that you have a set of points. So here, this is your P and this is your Q. An object P is so this is your P. An object P is indirectly density reachable from Q. Here also you are having two conditions. The first condition is same. Q is a core object. And the second condition is you are having you should have a set of points in between this Q and P such that this P2 is directly density reachable from this Q or P1. This P3 is directly density reachable from P2 and P4 is directly density reachable from P3. Then you can say that P is indirectly density reachable from Q. This is direct way. This is direct way. What is the direct way? First condition is common for both the cases. Q should be the core object. And the second condition is here that that point should lies within the epsilon neighborhood. That is a direct density reachability condition. If this is not lies within the epsilon neighborhood, something this is outside of epsilon neighborhood range, then when we can call that A should be directly density, that means indirectly density reachable from Q means there exists some set of points in between that A and Q such that each and every point in the middle should be densely reachable from one another, one followed by the other. Again, here also, in this case also, you can imagine the same magnetic field example. Suppose here is the magnet and this is the object, and suppose this is um I can I can explain by drawing a figure. No need to bother, right? So this is a magnet and this is its magnetic field, and I have another object is there. Another object is there, that is, so this is my Q and this is my P. Actually, P is not within the effect of that. That means within it is not within the magnetic field. But what happened here? Here is some another magnet is there, and its effect is up to this. Its effect is up to this, for example. And here is another magnet is there. Its effect is up to this. And here is another magnet is there. Its effect is up to this. What happened here? Indirectly, P is connected to this Q, right? Because of multiple magnetic effects, P is indirectly connected to Q. And I can say that P is indirectly lies within the magnetic field of Q because of the magnets present in middle of the Q and P. Like this, the same concept here also. So that is indirectly density reachable. And finally, you have the required one, density connected. When I can say that the points are density connected. So an object P is densely connected to the object Q with respect to epsilon and minimum points in a set of objects D if there is an object O belongs to D such that both P and Q are density reachable from O with respect to the epsilon and minimum points. So what's that? So here, this is what? Q is what in this example?
Core object, ma'am.
Core object. And A is there, and I am having another object, something, let us say this is P. I can say that A and B are densely connected. Sorry. Yeah. I can say that A and B are densely connected. What is the condition? A and B are densely connected. What is the condition? This should be there exists a core object, and the points A and B are directly density reachable from this core object. A and B directly densely reachable from this core object. Then you can say that A and B are densely connected. A and B are densely connected. Here. So an object P is densely connected with the object Q when if there exists another object O such that P and Q are densely reachable from O. P and Q are densely reachable from O. Density reachable ఎప్పుడు అవుతాయి? So if an object is densely reachable, so ఇక్కడ directly and mention చేయలేదు. So they are not mentioned directly density reachable. So that may be the directly or indirectly. So that is not the question here. Whether that may be directly density reachable or indirectly density reachable. If at all two points are directly or indirectly density reachable to that core object, we can say that those 2 points are densely connected. Or I will explain this concept with another example so that you can getting clear. Let me go through all the definitions once again. What is the epsilon neighborhood? What is the epsilon neighborhood of an object? So we need to first consider the radius epsilon. So if you consider an object, so with the radius epsilon, the boundary which we can draw, that neighborhood with the radius epsilon is called as an epsilon neighborhood of an object. And when we can call an object as a core object, there exists some minimum number of points given provided. So if at all there are certain objects present in the epsilon neighborhood of an object which satisfies the minimum number of points. So we are having greater than or equal to that minimum number of points exist in the epsilon neighborhood of an object, then that object is called as a core object. And how can you say an object is densely reachable, directly densely reachable from an object? If you say that P is directly densely reachable to an object Q, there are two conditions. First condition is Q should be a core object, and the second condition is P should lie within the epsilon neighborhood of Q. That is directly densely reachable condition. What is the indirect density reachability? That means the reachable condition. What is it? Here also, if you say that P is indirectly densely reachable from Q, the first condition is Q should be a core object, and the second condition is there exist certain points in between P and Q such that each point, that means P1 is densely reachable from P2, P2 is densely reachable from P3, and so on. Then we can say that P is indirectly densely reachable from Q. And what is the last one, an important thing? Density connected. So if you say that 2 points are densely connected, there exists certain core object. Like I said, this is O, and the two objects P and Q are indirectly or directly densely connected to that O. If O should be the core object, and this P is densely connected to O, either directly or indirectly, and that Q is also densely connected to this particular O, then we can say that this both P and Q are densely connected. So here we need this particular thing we need. So we know that P and Q are densely connected. So that P and Q along with this O can form a cluster. Why? Because in DBSCAN, look into this last line. It defines a cluster as a maximal set of the densely connected points. So all the densely connected points it need to gather and it forms a cluster with it. So that is our ultimate target. So let me take another example here. So here some objects are labeled as Q, M, P, S, O, and R, and given min points are 3. So identify all the core objects first. Just identify all the core objects. Identify all the core objects. We're almost at the end of the topic. Make it fast.
M P O.
Let me note down. M
P
P O.
O.
Imudena.
Yes, ma'am.
So let me check. So Q is there, and within the neighborhood of Q, only 2 points are there. So this is not the core object. Consider M, and within the neighborhood of neighborhood of M, we are having 5 objects, right? So this is the core object. And here P is within the neighborhood of P. We're having 4 objects. So P is also there. And for S, we're having only 2 objects. So S is not there. For O, we are having 4 objects. So O is also there. And in the case of R, we are only having 3 objects. So R కూడా వస్తుంది కదా వస్తుందా రాదా
S కూడా వస్తుంది మ్యామ్. S లో 4 ఉన్నాయి మ్యామ్.
ఒక నిమిషం R చేద్దాం. R అయితే వస్తుంది కదా. S వస్తుందా?
No ma'am.
S రాదు. So R, we are having 3 objects in the epsilon neighborhood of the R because this is the neighborhood, right? So we are having 3 objects. So we can call R as an epsilon neighborhood. That means core object. So these 4 are the first identification that we need to identify first. These 4 are the core objects. Some other core objects are also there, but we are only considering the labeled objects for the sake of understanding, right? And after that, density, what? Density, directly density reachable points we need to identify. So is P is directly density reachable to M? Is P is directly density reachable to M?
Yes, ma'am.
ఎలా చెప్తాం? How?
M is core object and
Yes.
P అనేది M యొక్క ఎప్సిలాన్ నైబర్హుడ్ లో ఉంది.
ఉంది కాబట్టి we can say that P is directly reachable to M. Similarly, M is directly density reachable to Q.
Yes, ma'am.
No.
M.
Why?
Oh,
Because yes, first and foremost condition, Q should be a core object.
Q is not okay.
Yes, but here Q is not a core object, so we can't say like this. If Q is directly density reachable to M, so here we have identified P is directly density reachable from M. I'm asking Q is directly density reachable from M or not? Yes or no?
Yes, ma'am.
Yes,
M
why?
is
Because
core
M is
point
core,
and Q
yes,
is within the epsilon.
within the epsilon neighborhood of M. So from this, can I say that P and Q are densely connected?
Yes, ma'am.
Yes, because what is the condition? If two objects are densely connected, they should be directly they should be densely reachable from the another object wo in the sense here in case of M. So I can form cluster like this. With this density reachable for points, I can form cluster. So here come here. So here this O is reachable from this point, right? Right or no? Because all these points are core objects, no doubt at all, consisting of more than 3 elements. Or let us label it. Some A is there, some B is there, label the points. Some C is there. So every point is a core object, core point here. ABC is also core object. So O is directly density reachable from A, right?
Yes, ma'am.
Or A is directly density reachable from O. And B is directly density reachable from A, right?
Yes, ma'am.
Similarly, R is directly density reachable from B. Yes or no?
Yes, ma'am.
Yes. That means here A is density reachable from O and B is density reachable from A and this R is density reachable from B. I can say that R is indirectly density reachable from O. Right or no? The second condition I'm talking about. Because R is not lie within the epsilon neighborhood of O. But there exist some points in between R and O which are density reachable, directly density reachable from one another. So I can say that R is indirectly density reachable from O, right or not?
Yes, ma'am.
This is the case. So since like this only, you can go with the density connected points. So here O R yes, all are density connected points. Let us check that. O R S. So here this S O R. Let me clear the screen first. ఇంకొక 2 minutes లో టాపిక్ అయిపోతుంది అందుకనే కంటిన్యూ చేస్తున్నాను ప్లీజ్ బి పేషెంట్ సో హియర్ O R S are directly densely connected, not directly. These three are densely connected. So what is the condition for densely connectivity? Densely connected points ki condition enti? They should be, if R and S are densely connected, they should be density reachable
Densely reachable to a point O.
with another point, another core point. Since if you observe, these two are densely connected already. These two are also densely connected. Why? Because all these are density reachable points. So we can form cluster with by connecting all these density reachable points. Here you have cluster like this. So what is the shape of the cluster here? What is the shape of the cluster? There is no shape, right? So with this particular DBSCAN algorithm, you can form the arbitrary shaped cluster. Suppose if you stick with the previous clustering algorithm, it only allows it only allows to have clusters of spherical shapes. That means you can't actually join the nearest points of the cluster. That means you maybe by following the previous examples, previous clustering algorithms, you may exclude those remaining objects, even though they are belonging to the same cluster. Whereas here, in case of density-based DBSCAN, here you can collect all those points and you can form different kinds of clusters. Whatever may be the shape, you don't bother about that. If at all a point belongs to that particular cluster based on the density and based on the epsilon neighborhood and based on all the conditions, if they are density connected, you can club that point to this cluster. Like that, you can form different spherical shaped clusters. And here you can have this slide. This is the last slide of this DBSCAN. So here DBSCAN, how does DBSCAN find the cluster? So this DBSCAN searches for clusters by checking the epsilon neighborhood of each point in the database. So first we need to find out the epsilon neighborhood of each and every point. That is the first step. If the epsilon neighborhood of a point P connects more than minimum points, a new cluster with P as a core object is created. So if at all in the epsilon neighborhood of a within the epsilon neighborhood of a object, if at all you are having more than min points, if at all you are having that, you can form a cluster initially. Don't bother about the connected points, densely connected points, directly reachable. Don't bother about that in the initial stages. If at all it satisfies the minimum number of points, if at all that is a core object, if at all P is a core object, you can form a cluster with that core object by considering all the epsilon neighborhood points. That is the first step. And what is the next step? DBSCAN then iteratively collects directly densely reachable objects from these core objects, which may involve the merge of a densely reachable cluster. So this process terminates when no new point can be added to any cluster. So first step is to identify the object, any object, to take the object and identify the epsilon neighborhood of it and identify number of objects lies within the epsilon neighborhood of it and identify whether it is a core object or not. So if it is a core object, so form a cluster with all the objects present within the epsilon neighborhood of that particular object. సో ఆ పర్టికులర్ ఆబ్జెక్ట్స్ ఏవైతే వాటి ఎప్సిలాన్ నైబర్హుడ్ లో ఉన్నాయో వాటితో ఒక క్లస్టర్ ని ఫస్ట్ ఫామ్ చేయాలి. అండ్ ఆఫ్టర్ దట్ గ్రాడ్యువల్లీ యూ నీడ్ టు ఐడెంటిఫై వాట్ ఆర్ ఆల్ ద పాయింట్స్ విచ్ ఆర్ డైరెక్ట్లీ కనెక్టెడ్ టు దిస్. After that, what are all the points which are indirectly connected to this? And after that, you need to identify what are the densely connected points. And finally, like this, you need to expand the size of the cluster and shape of the cluster. And finally, you need to add all the densely connected points to that cluster. And this process is repeated until there is no new point is there to be added to that cluster. Like this, you can generate the clusters in case of DBSCAN. So here we have finished all the clustering algorithms and we are only one topic left in the fourth series, outliers, and we'll discuss in the next class. And advance happy year to all. Bye bye. Take care.